Hybrid renewable energy systems represent a sophisticated integration of multiple renewable energy sources designed to provide a more reliable, efficient, and sustainable power supply than single-source systems. At their core, these systems combine two or more renewable technologies, such as solar photovoltaic, PV panels, wind turbines, hydroelectric generators, biomass converters, or geothermal units, often augmented by energy storage solutions like batteries or pumped hydro storage. The primary goal is to mitigate the inherent intermittency of individual renewables, solar power's dependence on daylight and clear skies, or wind's reliance on consistent breezes, by leveraging complementary characteristics. For instance, solar energy peaks during the day, while wind often strengthens at night or in cloudy conditions, creating a synergistic effect that ensures more consistent energy output. These systems can operate in standalone, off-grid modes for remote areas or be grid-connected to enhance overall grid stability. The concept has evolved from early experimental setups in the 1970s, driven by oil crises, to modern implementations supported by advanced control systems and digital technologies. In essence, hybrid renewable energy systems embody the transition toward a diversified energy portfolio, reducing reliance on fossil fuels and addressing climate change imperatives while adapting to local resource availability. The architecture of a hybrid renewable energy system typically includes several key components that work in tandem to generate, store, and distribute power. Renewable energy generators form the foundation. Solar PV arrays convert sunlight into direct current, DC electricity via the photovoltaic effect, while wind turbines harness kinetic energy from air movement to produce alternating current, AC, through electromagnetic induction. Hydroelectric components, if included, use water flow to drive turbines, and biomass systems combust organic materials like agricultural waste to generate steam for electricity production. Energy storage is crucial for balancing supply and demand. Lithium-ion batteries store excess energy chemically, offering high efficiency, around 90%, and rapid response times, whereas pumped hydro storage pumps water uphill during surplus periods and releases it through turbines when needed, providing large-scale, long-duration storage. Power electronics, including inverters and converters, ensure compatibility between DC and AC sources, while an energy management system, EMS, often powered by artificial intelligence, optimizes operations by monitoring weather forecasts, load demands, and component performance to decide when to draw from which source or storage unit. In some configurations, a backup diesel generator is incorporated for ultimate reliability, though this hybridizes with non-renewable elements, blurring the line with fully renewable systems. This modular design allows customization based on site-specific factors like geography, climate, and energy needs, making hybrid systems versatile for applications from rural microgrids to large-scale utility plants. One of the most compelling benefits of hybrid renewable energy systems is their enhanced reliability and ability to provide uninterrupted power supply, addressing the primary drawback of standalone renewables. By diversifying sources, these systems reduce the risk of total blackout during periods when one resource is unavailable. For example, in regions with variable weather, solar can compensate for low wind days and vice versa, achieving capacity factors up to 60–80% compared to 20–40% for single sources. This complementarity not only minimizes downtime, but also optimizes land use and infrastructure, as shared components like transmission lines and inverters lower overall redundancy. Environmentally, hybrids significantly cut greenhouse gas emissions by displacing fossil fuel-based generation. A typical solar-wind battery system can reduce CO2 output by 80–90% over its life cycle compared to coal or gas plants, contributing to global net zero goals. Moreover, they promote energy security by decreasing dependence on imported fuels, particularly in island nations or remote communities where fuel logistics are costly and vulnerable to supply disruptions. Economically, while initial costs are high, long-term savings accrue from free fuel sources and minimal operational expenses, with levelized costs of energy, LCOE, often falling below 0.05 per kilowatt-hour in favorable locations, making them competitive with traditional power. Beyond reliability, hybrid systems offer improved efficiency through intelligent integration and advanced controls. Energy management systems use algorithms to predict and allocate resources, maximizing output while minimizing waste. For instance, excess solar power can charge batteries during the day for evening use, or be used to produce hydrogen via electrolysis for longer-term storage. This efficiency extends to grid services where hybrids can provide ancillary benefits like frequency regulation and voltage support, enhancing overall power quality. In off-grid scenarios, such as rural electrification in developing countries, hybrids enable access to electricity for education, healthcare, and economic activities without extending costly grid infrastructure. Socially, they create jobs in installation, maintenance, and manufacturing, fostering local economies and skill development. Additionally, by reducing air pollution from fossil fuels, hybrids improve public health, lowering incidences of respiratory diseases and associated medical costs. In essence, the multifaceted benefits position hybrid renewable energy systems as a cornerstone of sustainable development, aligning with United Nations Sustainable Development Goals for affordable clean energy and climate action. However, the deployment of hybrid renewable energy systems is not without significant costs, beginning with substantial upfront capital investments. Designing and installing a system requires purchasing multiple components. Solar panels might cost less than $0.50 per watt, wind turbines $1,000 to $2,000 per kilowatt, and batteries $100 to $200 per kilowatt hour of capacity, leading to total costs ranging from $50,000 for small residential setups to millions for utility-scale projects. Site assessments, engineering, and permitting add 10 to 20% to the bill, while integration challenges, such as synchronizing different voltage outputs, necessitate expensive power electronics. In regions with limited infrastructure, transportation and labor costs escalate further. Operational and maintenance expenses, though lower than fossil systems, include periodic battery replacements, every 10 to 15 years, and turbine servicing, averaging 1 to 2% of capital costs annually. Financing these systems often involves loans or incentives like tax credits, but interest rates can inflate effective costs. Despite this, cost-benefit analyses show payback periods of 5 to 10 years in high insulation areas, driven by fuel savings and revenue from excess power sales. The economic viability of hybrid systems is further influenced by location-specific factors and scale. In sunny, windy locales like the American Southwest or Australian Outback, LCOE can drop to about $0.50 per kilowatt hour, but in less favorable climates, it rises to less than $0.20 per kilowatt hour, necessitating subsidies. Large-scale projects benefit from economies of scale, reducing per-unit costs by 20 to 30%, but small rural installations face higher relative expenses due to fixed overheads. Storage adds significantly to costs. Pumped hydro at $1,500 to $3,000 per kilowatt hour installed, but enables energy arbitrage, selling power during peak prices. Net present value, NPV calculations often reveal positive returns, with internal rates of return exceeding 10 to 15% when including environmental externalities like carbon pricing. Government policies, such as the U.S. Inflation Reduction Act's tax credits up to 30%, can offset 20 to 40% of costs, making hybrids more accessible. Overall, while costs pose a barrier, declining technology prices, solar PV down 89% since 2010, promise affordability. Despite their advantages, hybrid renewable energy systems face notable disadvantages, starting with technical complexity. Integrating diverse sources requires sophisticated EMS to manage power flows, which can fail due to software glitches or incompatible hardware, leading to inefficiencies or outages. Intermittency, though reduced, persists. Extreme weather events like prolonged calm or overcast periods can strain storage, necessitating oversized components that inflate costs. Site dependency is another challenge. Optimal hybrids demand locations with complementary resources, limiting deployment in urban or resource-poor areas. Scalability issues arise when expanding systems, as adding capacity may require grid upgrades or land acquisition, facing regulatory hurdles. Environmentally, while low-emission, hybrids aren't impact-free. Wind turbines can harm bird populations, solar farms disrupt habitats, and battery production involves mining rare earths with ecological costs. Social and economic disadvantages further complicate adoption. high initial costs deter low-income communities, exacerbating energy inequality despite long-term savings. In developing regions, lack of skilled workforce for maintenance leads to underperformance, with systems sometimes abandoned due to parts shortages. Policy inconsistencies such as changing subsidies create investment uncertainty. Moreover, hybrids may not fully eliminate fossil backups in some designs, perpetuating some emissions. Aesthetic concerns like visual pollution from turbines spark local opposition, delaying projects. Finally, life cycle management, recycling batteries or decommissioning sites, poses waste challenges, potentially offsetting environmental gains if not handled properly. To illustrate the practical application of hybrid renewable energy systems, consider case studies that highlight their effectiveness in diverse settings. In the island of Graciosa, Portugal, a hybrid wind-solar battery system powers the entire community, achieving 65% renewable penetration and reducing diesel use by 95%, saving millions in fuel imports annually. Similarly, in Australia's Coober Pedy mine, a solar-wind-diesel hybrid with storage cuts energy costs by 70% and emissions by 9,000 tons yearly, demonstrating industrial viability. In rural Bangladesh, a PV biogas hybrid for a health center provides reliable power for medical equipment, with LCOE 35% lower than solar alone and zero unmet load. These examples underscore how hybrids adapt to local needs, from isolated islands to mining operations, delivering economic and environmental returns. Looking toward 2026 and beyond, future trends in hybrid renewable energy systems promise greater integration with emerging technologies. AI-driven EMS will optimize operations in real time, predicting weather and demand with 95% accuracy, boosting efficiency by 15 to 20%. Hybrid PPAs combining solar, wind, and storage will dominate corporate procurement, offering stable pricing amid volatility. Global additions may slow post-2025 peaks, but focus shifts to storage hybrids, with BESS installations reaching 15 gigawatt in the US alone. Policy evolution like extended tax credits will accelerate adoption, while supply chain reshoring mitigates risks. In India and China, massive hybrid projects will drive the bioeconomy, incorporating green hydrogen for long-duration storage. Expanding on the definition, hybrid systems can be classified as on-grid or off-grid, with on-grid variants feeding excess power back to utilities for revenue, while off-grid ones serve isolated loads like remote villages. Configurations vary. PV wind battery is common for residential use, achieving 90% self-sufficiency, whereas utility scale might include hydro for base load.